All right, good afternoon, everyone. For our brown bag regulars, you'll notice that we have a slightly different setup today, and that's because we have a Delta Independent Science Board meeting starting at 1:15. You're welcome to stay for that meeting, but since we need to set up, we ask that you leave this room immediately following the brown bag. Thank you. So the Brown Bag Seminar Series is hosted by the Delta Stewardship Council Delta Science Program, the CDFW Watershed Restoration Grants Branch, and the Surface Water Ambient Monitoring Program. That's okay. Please silent your phones, and if you need to use the bathroom, take a key from the wall and go left after you exit the doors. Today's speaker is Dr. David Schoellhamer, research hydrologist for the U.S. Geological Service. He earned a bachelor and master's degree in civil engineering from UC Davis and a doctorate in coastal and oceanographic engineering from University of Florida. From 1987 to 1993, he studied sediment transport in Tampa Bay, Florida. And he has studied sediment transport in the San Francisco estuary since 1993. He also taught classes on sediment transport and hydrology of the Bay Delta at UC Davis. The movement of sediment is determined by flow dynamics and transport processes, which he will discuss today as part of our 2016 State of Bay Delta Science Seminar Series. The State of Bay Delta Science 2016 is a collection of peer-reviewed articles that summarizes the scientific understanding of the Sacramento-San Joaquin Delta. Dr. Schoellhamer's article on flow dynamics and transport was published in December in the online journal San Francisco Estuary and Watershed Sciences. So please join me in welcoming Dr. Schoellhamer.
Well, thank you, Nir. It's great to be here. So if we can have the next one. Okay, here we come. So thank you. It's a great week to be down here talking about transport processes and flow dynamics with everything that's going on. It was outstanding planning by the science program to have me come down and discuss that this week. So I'd first like to just acknowledge my co-authors, Scott Wright, Steve Monismith, and Brian Berger-Mosky, who helped me a tremendous amount write this paper on transport processes and flow dynamics. What we mean here with transport process and flow dynamics, what we're talking about, I'd just like to define these terms so we're all start on the same page. Flow dynamics is basically how water moves through the channels of the delta, how water gets around. And then transport is how all the stuff in the water moves with the water, since it can move slightly differently. So transport is how these things move. The things that we're moving are, the fancy term is constituents for this stuff, which includes things like salinity, heat, oxygen, nutrients, contaminants, organic and inorganic particles, are all the things that are moving with the water. So if you're concerned about these items, these constituents, you then need to know how they're moving through the system to understand their behavior in the delta. The geographic scope of this particular work is the delta, how the watershed affects the delta, and how the delta interacts with the bay and the ocean. So our primary focus with the work we decided was specifically on the delta. Also, these papers are really intended to summarize advances in the last 10 years. We try to focus on more recent advances that have taken place for the State of Bay Delta Science papers. So why this matters is I started making a big laundry list of why you all should care about transport and how things move around the delta, but I just decided to simplify it down to one constituent, just basically salinity. One of the big issues, obviously, with the delta is how far is salinity going to come into the delta, and where is that line of salinity? And there's some different examples here. So salinity is sourced from the ocean. It's basically ocean water that's transporting, pushing up into the delta, and how far it goes is determined by the physical processes and how much fresh water is coming out of our reservoirs and out of our river system to repel that salinity. So why transport matters, you can simply boil it down to the issue of salinity. How far salinity intrusion is going to be is determined by these transport processes. And therefore, freshwater withdrawals from the delta for farming and for export and also any salinity as an ecological variable where certain species will be able to live. So in this particular report, what is not in the report is we don't consider it to be a comprehensive review of all literature. We did not try to cite every paper. My apologies to you if I didn't cite your paper. Sorry about that, but we already had enough citations in there. We do not present a conceptual model of flow dynamics and transport. These are given elsewhere in references that are given in the report. We do not discuss fish movement. We don't have fish as one of our constituents, although it could be because the State of the Bay Delta Science has 2 other papers that specifically discuss fish movement, so we didn't feel we needed to repeat that. And we also don't get much into the idea of numerical modeling. There's a separate paper by Michael McWilliams and others that go into the specifics of numerical modeling, and so that's covered in another paper. This particular talk, I'm going to give sort of my highlights from the paper. There's really too much in there to cover in the short amount of time here. Because I'm talking and my background is in sediment transport, I have to confess that I have somewhat of a sediment transport bias for what I'm presenting here. But you can have one of the other co-authors and maybe get a very different talk given. The paper gives all of the relevant literature and more details than I'll be able to give here, so I just encourage you to read the paper in the online journal. Also in this talk, there's some new information, some new publications, and some new ongoing work that in a couple places that I just wanted to show you also. So if you've already read the paper and digested it all, don't fall asleep because there will be a couple new little tidbits I'll throw in at you. So for the paper, we were trying to organize all these references and information that's been generated over the last 10 years. So we came up with what we call sort of a conceptual framework for how transport works in the delta. And this could be, it's too simple of a thing to actually call a conceptual model, so we call it a conceptual framework. So in this slide, the white arrows here are supposed to represent transport. The 2 circular arrows represent mixing. One of the things that transport does is mixes different types of water, ocean water and river water, for instance. Also, the arrow going from right to left is supposed to represent the through transport of water as water moves from the watershed to the ocean. And so that sort of represents the net transport within the delta. So the white arrows here again represent the transport processes. These are affected by a number of drivers shown by the other colors here. One of those drivers is the oceanic forcing, basically the forcing that comes from the ocean, and this is shown as an exchange between the delta and the ocean, since there's sort of a 2-way exchange of information. The brown arrow, an appropriate color for this week, represents the fluvial inputs, basically the inputs from the watershed coming into the delta. Those are modified by our reservoir system, which is sort of the gray little dam there, as an anthropogenic effect, an anthropogenic driver. Humans also affect mixing in the delta with things such as gates and barriers. We also have, obviously, water withdrawals that are an anthropogenic effect on the delta. Other forcing is atmospheric forcing, storms, solar radiation, and wind shown here, and also biogeochemical forcing. Basically, biomass within the delta, marsh grasses and such affecting transport. Also geochemical processes that can act as a source or a sink for the constituents that we have of concern. So this is the conceptual framework that I'll sort of structure some of the findings around. I'll sort of classify these in their sort of primary categories, but as I'll show many examples, often the things we care about have multiple drivers affecting the particular constituents. So I'll start off with the describing for you some of the oceanic forcing, how the ocean affects the transport within the delta, and some of the new findings for that. And the main story here is, if you get nothing else out of the talk today, it's all about the tides. Tides. Tides drive so much of the transport within the delta. As an example of this, from my colleague at USGS, Lisa Lucas, I have an example here, so I'll start showing this video. The video here is to demonstrate for you the importance of the tidal motion. And so on this video, there's a red dye being continuously released up at Verona, which is off the map here. So you now see it coming down the main stem of the Sacramento River. This is for an October low flow. The delta cross channel located here is open, so water is moving into the central delta fairly quickly. Each frame has a 2-hour time step to it, so each image is separated in time by 2 hours. And I want you to focus on sort of the leading edge of the red dye coming down through the Sacramento River to see all of the tidal variability that takes place on a typical tide. For this simulation, there is pumping taking place down in the south at Clifton Court Forebay, so there is a net flow down to the southern delta. Things you may want to notice, for instance, the upper Sacramento River here, you can see quite a bit of tidal variability as what's now a sort of yellow plug of dye moves up from Liberty Island down into the lower Sacramento River with each tidal cycle. So again, quite a bit of tidal motion. This is what we know as the tidal excursion of several kilometers, water moving back and forth. Each change of color, the color you can think of as representing a concentration. So if you go out to collect a water sample, for instance, in the lower Sacramento River, sometimes the water is the light blue, sometimes it's sort of an orange, reddish color. And that represents changes in concentration that take place over just a couple of hours. So this is one of the challenges of collecting data in the deltas, that the tides change the concentrations tremendously over the course of a few hours. You can get a water sample, and a couple hours later, you may have a very different concentration at that location. Other places you can see some variability is here at where the McCollum River comes into the San Joaquin. There's quite a bit of mixing that takes place at junctions. I'll talk more about this in a moment. But the key junctions like the 3 Mile Slough and the McCollum River coming into the San Joaquin River, you can see here sometimes San Joaquin River pushing up in the McCollum, sometimes Sacramento River coming out of the McCollum into the San Joaquin. So again, quite a bit of action takes place at these junctions. With the pumping taking place and the net tidal flow, you can see now this some of this dye from the Sacramento River has moved into Clifton Court Forebay, and also the pumps coming through the Old and Middle River channels. And as you look down there, even in this simulation, well, I've been talking too much, but as you could see that dye moving down through the South Delta, there was also quite a bit of tidal variability taking place down in the South Delta. So this is throughout my career, several times, I don't mean to pick on chemists, but sometimes chemists will say, gee, we went out and collected some samples, and we went back a day later, and it's completely different, and gee, it seems like these tides are important. And yes, the tides are very important for collecting the water samples. So if you get nothing else out of the talk today, just the importance of the tidal motion. I would say in the last 10 years, this appreciation has grown. One way this concept is we phrase this concept in the paper, is that the idea that the transport is really driven more by the tidal motions I've just shown you than the tidally averaged flow. So for this simulation I've shown, this is the tidally averaged flow for the simulation I just showed, with water coming down the Sacramento River through the Delta Cross Channel, and ultimately some of that winding up down at the pumps in the South Delta. So this is the tidally averaged model of how transport works in the Delta. But in reality, as you can see from the simulation, from the animation, it's really the tides that are driving so much of the transport. And I would say we really felt that in the last 10 years we've gained a much better appreciation of how transport works in the Delta due to this tidal variability. One of the reasons for that is dispersion at junctions that we mentioned in the report. Here is just an example from where Georgiana Slough comes into the McCollum River. These are some drifter results showing the paths of drifters released at this junction, and they often get trapped here, and what numerical modeling shows is a recirculation zone at this junction. So for instance, water coming out of Georgiana Slough carrying a constituent of concern to you, some of that will get caught up in this recirculation zone for a while and then leave the recirculation zone. this causes a net dispersion, the smearing of that signal from Georgiana Slough into the McCollum River. And this is a very detailed hydrodynamic feature, but it can be very important for the dispersion of these constituents in the system. This also implies that in terms of numerical modeling, simple one-dimensional models aren't able to simulate this kind of effect, this dispersion that takes place at the junction, because they assume the junctions are well mixed. And so the net result then is that multidimensional models are better represent mixing at the junctions. One tool we have that's greatly increased in the past 10 years for studying this mixing by the tides is the great advances in the acoustic and optical instrumentation that we have in the system and with our technology. So we have acoustic instruments that can measure velocity continuously, and a large network of those instruments now done by my colleague John Bureau at the USGS. We also have optical instruments that can measure a wide range of water quality parameters in the delta and do so continuously. So this tremendous increase in the technology has really increased the data we can collect and better improved our understanding of the tides and how tides affect the delta. One example of this, just to continue this theme of tidal and tidally-averaged flow, this is at Mallard Island at the junction of where the delta essentially becomes the bay, if you will. The gray line here is the tidal flow, averaging about 300,000 cubic feet per second tidally, and then the tidal average flow is a couple of order magnitudes smaller than that. So we have very small tidally average flows, but very large tidal flows. So a tremendous amount of tidal energy and water movement with the tides compared to the tidally averaged situation. In terms of comparing measured flow with calculated delta outflow, we can measure the delta outflow or infer the delta outflow from the flow gauges that we have. We also have calculations of what delta outflow are with the DWR day flow program. That essentially is a conservation of mass of water calculation of what delta outflow should be. What we find is that for high flows in this upper part, or for most flows, the conservation of mass and the measurements do a really good job comparing with one another. However, for the low flows down here in the lower graph for flows up to 10,000 cubic feet per second, there's a lot of scatter that takes place there. And one of the reasons for this is the differences in water levels within the delta. Changes in the ocean forcing can cause slow changes in water level. Also wind speed, as wind blows into the delta, that can cause a setup of water level in the delta and affect flow in and out of the delta as the water level changes. So for these low levels of freshwater discharge, the calculations assume what we, us engineers, call a rigid lid, that the water level is constant, when in fact the water level in the delta, the mean water level, is varying, and this causes changes in the flow that we can observe with the network of sensors that we do have. So for management, one implication of this is that when you have the low flows, which are sort of the most critical flows to manage well, we have the most uncertainty in what that outflow actually is. Tides also affect other things. I want to show an example of how they make turbid water. So up in the Cache Slough area of the delta is where we typically see the highest turbidity, the highest suspended sediment concentrations. And in studies that we've done, we found the reason for this, the mechanisms that cause this, is that up in the Cache Slough area we have this network of dead-end channels and very low freshwater flow. As the tides move up into these fairly shallow channels, their character change, and there's an asymmetry in the tides. The floods and the ebbs are not equal. We actually see greater flood velocities than ebb velocities. These greater flood velocities favor sediment transport in the landward direction, and this causes, as these arrows show, a net transport of sediment up into the Cache Slough area where this sediment becomes trapped. One reason it becomes trapped is that we have limited tidal excursions up there. The tides only move back and forth so many kilometers. So a sediment particle that starts a ebb tide up in the upper Cache Slough doesn't get all the way out to the Sacramento River. By the time the tide stops, it's only moved as far down as lower Cache Slough. The tide reverses and moves that particle back upstream. So we have this trapping mechanism in Cache Slough that traps this sort of massive sediment up there, and with repeated cycles of erosion and deposition, we have higher concentrations of suspended sediment concentration and therefore turbidity up in Cache Slough, which is considered a favorable environment for creatures that like turbidity, such as the delta smelt. Now, sort of looking at a historical view of this is that these isolated dead-end sloughs create this, what we now consider this desirable habitat. They were once a prominent feature of the delta. When we look at the historical ecology work that SFEI has done in the lower left corner here, there's a tremendous number of these small dead-end sloughs with large lengths and therefore relatively small tidal excursions that are ripe opportunities essentially to trap sediment and turbidity. And except for this area of Cache Slough that we have now, the delta is really just this series of interconnected waterways with very little isolation that is present. And so one thing we observe from this particular work is that creating these isolated channels are a feature of the delta that does not exist and may be useful for restoration. Another effect of the ocean on transport is sea level rise, that as sea level rises, certain processes will become more prominent. One of those is stronger gravitational circulation, essentially the landward flow of denser water along the bottom. That increases with theoretically, the water depth cubed. So as you increase sea level and increase water depth, you get stronger gravitational circulation. The result of this is that the upstream flux of sediment, the upstream movement of salt will become greater as sea level rises, and therefore more fresh water is needed to maintain the salinity fields at the positions it is now, basically our X2 standard. And also, therefore, there would be less water for diversions. One thing I just wanted to point out here is that this is a mechanism of using reservoir releases to control salinity as sort of an anthropogenic mechanism or anthropogenic feedback to take the oceanic conditions and sort of move those up to the watershed. Normally that's only done through atmospheric forcing, but as humans, because we regulate the reservoirs to counter the oceanic forcing, we're sort of regulating the watershed and fluvial environments based upon the ocean. So we create this sort of additional feedback loop between the ocean, from the ocean to the fluvial and watershed systems. Also, to point out that even in this example, this is an example where we have several interacting drivers, the oceanic forcing, the anthropogenic forcing, and the fluvial forcing, all interacting with one another. So far, I've been talking about the effect of the ocean on the delta, but there is the bay downstream from the delta. So I wanted to give one example of how the delta affects the bay. And to give you sort of the extreme example of this, I'll go all the way down to South San Francisco Bay, where we measure the movement of sediment at the Dumbarton Bridge, way down there near San Jose. And for these data from the spring, this is a plot of delta outflow, monthly delta outflow during the spring in millions of cubic acre feet, versus the sediment flux in kilotons, monthly values at the Dumbarton Bridge for several different water years. And what we see for these two sets of water years is a fairly good relation of increasing sediment flux out of South San Francisco Bay as delta outflow increases. And so there's a linkage between delta outflow and sediment movement in South San Francisco Bay. There's two sets of data here because with the drought from water years 2013 to 2016, the sediment concentration in South Bay has actually increased, possibly due to less of this flushing taking place. So that's why we have the two different sets of lines here for these two different periods, sort of earlier drought and later drought. But there is as has been hypothesized for decades now, a clear relation between flushing of South San Francisco Bay increasing with increased delta outflow in the spring. To give you a demonstration of this, some fairly recent work to show how this works is this white box is what we consider a control volume for lower South San Francisco Bay, and there's a number of sediment fluxes going into and out of this control volume. This arrow here represents the local tributaries. There is erosion and deposition. There is gravitational circulation that takes place between Central Bay and South Bay that transports sediment in and out of South Bay. Generally, the circulation is in near the bottom where the sediment concentrations are greater, so this causes a net transport of sediment into lower South Bay. Also, for lower South Bay, the sediment concentrations tend to be greater than Central Bay, so there is a dispersive flux out of lower South Bay towards Central Bay. So if we have an equilibrium situation like this where the sediment concentration is relatively constant and these fluxes are all in equilibrium, and then we perturb these fluxes by having a delta outflow event and decreasing the salinity in Central Bay, which is happening right now, actually. So that decreased salinity decreases the density difference between Central and South Bay, and the result is we have less gravitational circulation taking place. So we perturb this system by decreasing the gravitational circulation when we have a delta outflow. The net effect of this is with the gravitational circulation directions, we have less sediment coming into South Bay. So with less sediment coming in and disturbing the equilibrium, the concentration in South Bay goes down, and the result of that is that we have less deposition and less dispersive flux out. And that's sort of how South Bay then compensates to establish, if you will, a new equilibrium. Now, if you're a restoration project in South Bay, for instance, the South Bay Salt Pond project, a decrease in deposition may be of concern or interest to you. So this, again, is an example of how delta affects the bay ranging all the way down to South Bay. So there certainly are downstream effects of what happens in the delta. What happens in the delta doesn't stay in the delta, is the bottom line. So moving on to the next sort of main driver is the fluvial driver, basically how the watershed affects the delta, with our brown arrow here. And, of course, this week there's a great example of this. This is me at Hogback Island boat ramp yesterday. During a high tide, we have fluvial forcing that increases the water level. And then we launched the boat just fine at the boat ramp and get back. And we all had looked at the tide tables but realized that, well, there's a high tide when we get back in the afternoon. So this is the boat ramp at the high tide with a few extra inches of water on top of things. So we do have these interacting drivers, high water due to the fluvial inputs and all that nice brown water and debris. We had to move out for the boat ramp to be able to get our boat down there, in addition to the sea level and the tidal signal that's present there. So this is a realistic example of interacting drivers. Now, I mentioned the advances in technology for measuring flow and some constituents, and how that's important in the tidal environment where we have these tidals sloshing back and forth in these tidal signals. This also really helps us understand riverine signals, fluvial signals coming into the delta. This is an example from Brian Pellerin, some nitrate samples collected on the San Joaquin River. A number of years ago, I believe the samples were collected every 3 or 4 hours. And a lot of samples are collected over a short amount of time. A lot of work goes into collecting these samples. And you look at this figure and you see, well, it looks like a kind of a noisy linear increase in nitrate concentration. But they also deployed a continuous sensor collecting 15-minute data, and what looked like this sort of linear increase of concentration actually has quite a bit of pattern to it with the natural variability in the river. And so this demonstrates, even in the riverine environment, the importance of collecting the continuous data to observe these rapid changes that take place on the order of an hour or two, and the power of the continuous data compared to the discrete water sample type of data. One of the things we've learned about over the past 10 years a lot more about is the effect of what we call the first flush. And as the rain falls, the watershed becomes saturated, and at some point, it's typically a little after, I think it's about 8 inches of rain or so, all the rain that falls will run off the watershed. And this is sort of the first flush of sediment, material, contaminants, everything coming out of the watershed is what we call the first flush. So a lot of the sampling we do is, over the past 10 years, has been focused on the first flush. These are some examples from Scott Wright and Tara Morgan of the first flush. This is turbidity plot. The black line is at Freeport, up in the riverine part of the Sacramento River. The red line is at Rio Vista, down in the lower Sacramento River, and the blue line is turbidity at Mallard Island. As that pulse of turbidity, a pulse of sediment moves from the river down through the delta. Several observations here. If the slide will advance, there we go. Is the duration of this first flush is fairly short. Here, typically about a week or two. The bottom plot here is the tidally averaged discharge. So first flush lasts about a week or two. So if you're sampling on a monthly basis, for instance, you may completely miss the first flush or just get 1 point during it. So it requires a lot of sampling during a short amount of time, which is why almost all of my colleagues are out sampling today. That's where I was earlier this week, but I had to give this talk, so I'm here now. But this is the time to collect the samples because a lot of material moves during a short amount of time, and that's what we really need to catch to understand the movement of these constituents through the system. We also observe that there's a rapid change of the river input. The river input isn't constant, but even at Freeport, you can see spikes taking place here. This is probably inputs from different watersheds up in the upper Sacramento River being transported down the Sacramento River and showing up at Freeport, or the downstream end of the river environment. So the river isn't just sort of a monolith that's putting out a constant concentration. It can vary tremendously too. Other things to note is that even though we have a first flush, a flow pulse going on, there still is tidal variability. You still have to deal with the tides. I showed an example from yesterday of tides mattering, and here at Rio Vista for these first flush data from 2011, I believe this was, you can see that there's still quite a bit of the tidal variability like I showed you in the animation. There also is diffusion that takes place. Basically, this comes down as a fairly sharp peak at Freeport, but as we go through Rio Vista all the way down to Mallard, that tidal sloshing back and forth, all that mixing at junctions takes these peak concentrations and spreads them out. And so what we wind up with at Mallard Island is a pulse that takes place over several weeks as opposed to just 1 or 2 weeks. So it tremendously spreads out the pulse of material coming down during this first flush. Other advances about the fluvial inputs is, one of the questions is, what is the historical conditions like? And I've worked with a graduate student up at Portland State, Hamed Maftakhari, and he was able to look at historical flow and sediment inputs. What he used is he was able to uncover water level data from the 1800s to basically provide better estimates of flow. This water level data is at the Golden Gate Bridge and in Sacramento, some old records that were collected by a physician daily over 30 years. And with the Golden Gate data, the freshwater flow out affects the tides. And so by calculating certain frequency tidal constituents and how those change in time, one can back calculate what the freshwater flow is and extend the instrumented record back in time to when water level was first collected at the Golden Gate beginning in the 1850s and 60s. And just some things to note here. This plot on the left here is the flow with days from water year days along this axis and years from 1850 to 1930 here. One thing to note is that from this instrumented record, the magnitude of the 1862 flood, which is bigger than any flood we have seen, and just always a cautionary note that there's always a bigger flood out there that could happen. In this case, at least in this instrumented record, the biggest flood on record is this 1862 flood. In terms of sediment inputs, with the flow information, we used the bathymetric change data that Bruce Jaffe at the USGS has collated to estimate then sediment inputs to generate that kind of bathymetric change, which are shown here. And you can see that with the sediment, and this is from 1850 to 2000, that sediment transport is largely determined by these very few large flow events throughout this record, and the magnitude of the 1862 flood, which was the largest flood and also had a tremendous erodible pool of sediment due to hydraulic mining. Also, you can see that since for the past several decades, there's been relatively little sediment input as that erodible pool has diminished. One result of this is in the Delta, some work that I've done with Erin Hester, where she looked at the monthly data from the IEP for total suspended sediment at 5 sites in the Delta, and looking at the average values there, and did a breakpoint analysis, which makes no a priori assumptions of what the data is going to do to find the best fits of lines and breakpoints where there's a sudden change in the data. And when she did this for the Delta, what she found is there were 2 significant breakpoints in 1983 and 1998, where there were large step decreases in suspended sediment concentrations centered around those years. Those years happen to be 2 of the bigger flow years with the El Nino flows. So what we observe here is a decrease in sediment concentration after these really, really big flows. This isn't a really, really big flow, but after those really, really big flows. And the result here is that basically sediment being washed out of the system, decreasing the erodible pool of sediment, and therefore decreasing the available sediment, the sediment concentrations. Another thing we found is that since the 1998 El Nino, that sediment concentrations in the Delta have continued to decrease with time through the present day. And there's been about a 50% decrease in the suspended sediment concentrations in the Delta since the 1998 El Nino. So one question that came up for us when I was part of the Cascade project is, will this decreasing trend of sediment continue? Will the Delta waters get clearer and clearer, or will they stay at roughly the turbidity they're at now? And these are a couple of scenarios we ran for different climate change scenarios. This is the historical record of sediment decrease, and these are the 2 options we considered, one being basically a constant sediment relationship with flow, and another a continued decrease of sediment concentration shown here. And the question often is which one of these scenarios will happen? Well, what we know in terms of the sediment supply from the watershed is that through the work we've been doing, that the sediment supply is in fact decreasing down the rivers, that the watershed and the estuary adjust to this decreasing supply. They adjust by decreasing the concentration and adjusting the bed elevations. And there have been a number of studies summarized in this paper to describe that. We also know that these rare large floods transport a lot of sediment, that these big floods are what's really important for moving the sediment. Also that we've observed these recent step changes in bed elevation and suspended sediment, and these are associated with the largest floods that have been experienced since hydraulic mining. And so the hypothesis we have to perhaps explain the future is that it is likely that the estuary and watershed are still adjusting, that concentrations, for instance, in the Delta can still continue to decrease, but the adjustment will happen as these steps that occur as we have larger and larger floods than previously experienced during the adjustment period. Another way of saying this is that larger and larger floods are needed to exceed geomorphic thresholds, essentially thresholds to move a tremendous quantity of sediment, and that between these larger floods we have periods of equilibrium, and these periods of equilibrium, relative tranquility, if you will get longer and longer with time. So let me move on quickly to some of the other drivers now of transport in the Delta, the anthropogenic and atmospheric drivers, which I'll combine here. While we're still on the sediment subject and the idea of sediment supply from the watershed, some of our previous work looking at the causes of reduced sediment supply. One is the diminished hydraulic mining pulse, basically less erodible sediment in the watershed. Another that we've documented is trapping behind dams, that the reservoirs trap sediment and essentially cut some of the sierras off from the watershed in terms of sediment transport. Well, my colleague at USGS, Michelle Stearns, found another mechanism recently with some modeling results as part of the Cascade project, where they developed a watershed model of sediment for the watershed. And they looked at different scenarios, including warmer temperatures. And what they found is that warmer temperatures have been causing, as we would expect, more rain and less snow. The effect of this change, one of the effects of this changing hydrology is that these peak flows that are so important for sediment transport have been decreasing. And so with these decreased peak flows, that has contributed to the reduced sediment supply that we've been observing. So we have not only anthropogenic causes of the sediment supply decrease, we have atmospheric causes also with a changing climate. Another note on the anthropogenic and atmospheric forcing is the timing of flows. Now, this has been, this slide here shows flow estimates, outflow estimates on the vertical axis and water year days on the horizontal axis. Some more work from Hamed at Portland State. The red line is for the present day, 1968 to 2008, and the blue line is for the 1800s. And this is actually based on the instrumental record collected at the Golden Gate Bridge. So again, measured the tides, back calculate the freshwater flow, and what we get are these two hydrographs here. So the observations from this is that, as previously noted or hypothesized, if you will, the modern inflow is about 35% less than the historical inflow. Basically, the area under the blue curve is greater than the area under the red curve. And the flow peaks are earlier than previously, about 100 days earlier in this century than in the 1800s. And this now is based on actual instrumented record and calculations from the instrumented record, not numerical modelings or assumptions. Finally, I wanted to discuss the biogeochemical forcing. One example of this is marsh restoration, which actually in some ways is an anthropogenic driver on the delta system. For instance, men planting restoration, planting of marshes to affect the transport. It can affect the transport in a number of ways. It changes the bathymetry and topography of the delta, which will affect how the tides propagate through the delta and therefore affect mixing and transport. Another effect here is on the marsh capturing suspended sediment. The marshes are effective sediment traps, and so are fluvial inputs of sediment that may increase marsh restoration. One of the ideas is to capture sediment, so that may increase the efficiency of sediment trapping within the delta. The marsh can also act as sort of a geochemical source or sink. For instance, the big concern obviously is with methyl mercury, that the marsh can be a source of methyl mercury for the delta. And so that's one way that marsh restoration can sort of affect the delta in several ways. Another effect of the biogeochemical effect I wanted to mention is the invasive aquatic vegetation that's been spreading throughout the delta. As I mentioned, that since 2000 or 1998, there's been a general decrease, continuing decrease in suspended sediment. One hypothesis that we have is that the aquatic vegetation, which has been growing during that time, has contributed to that decrease in the suspended sediment. Aaron Hester and I did a study looking at the long-term trends of turbidity in the delta and how proximal, how close they are to submerged aquatic vegetation. What we found is that at sites where there's a greater decrease in turbidity and suspended sediment, generally have more aquatic vegetation. And through some estimates in the paper, we were estimating that 21 to 70% of the declining turbidity trend is attributable to the vegetation expansion. Just one other note of that there is a new USGS project that I'm part of that's evaluating how aquatic vegetation affects turbidity and trapped sediment, and therefore also affects the sustainability of marshes, where if the sediment is moving into the marshes or moving into the vegetation as opposed to moving into the marshes. And this is a project that we are just sort of an internal USGS project, just beginning to try to evaluate these physical processes evaluate the effect of the vegetation on sedimentation processes. In the paper, sort of moving on, one of the things we address is the usual list of information gaps that we have. One that I just wanted to bring out in this talk is the concept of continuous flux-based monitoring, how helpful that's been for us and how helpful that could be for understanding how things move through the delta. We need the continuous monitoring, as I've shown several examples of today, to evaluate tidal processes because of the tremendous amount of transport that takes place due to the tides, also for episodic events. When you have big flows like this, it's really difficult to get instruments out now, but it's good if you have the instruments already in place. So the continuous monitoring is very helpful for getting the episodic events and the tidal variability. We say flux-based because typically a water sample tells you a concentration of your favorite constituent, how much mass per unit volume is there. The flux-based measurements, which include the water discharge, tell you how much mass of that constituent is passing a cross-section. And so with that, you can trace how much mass is, for instance, coming into the delta, coming out of the delta, or coming into a restoration project and out of a restoration project. And with that, you can develop budgets for constituents of whatever constituent you have of concern. So being able to make the sort of unit of quantification flux as opposed to concentration is very helpful for developing these constituent budgets, also doing things like total maximum daily load calculations. Also, this monitoring should be done on the landscape scale. As I've been trying to show, the watershed, the delta, the bay, and the ocean are all connected with one another through the natural progression of flow, through tides, through anthropogenic effects. And so to understand, throughout my career, I found that in order to understand what happens in the delta, for instance, with sediment, you need to look up into the watershed and understand what's happening in the watershed. So these environments are well connected. And this needs to take place over a long term, certainly greater than the decadal time scale. For instance, we're having at least a 1 in 10 year event now, and so a lot of long-term sampling is needed to capture these types of important events like we're having today. So with that, I just wanted to thank you all for coming, acknowledge again my co-authors who helped with this, and the Delta Science Program for supporting this work. So thank you, and I can have a few minutes, I think, for questions. And for the web folks, we have a microphone, and we have a question up here.
One of the conclusions you made was that warming temperatures leads to more rain, less snow, which is obvious. But then how does that translate to a lower in the peak flow? Because it seems to me it's the opposite, because you got liquid runoff. The reservoirs have to release more often and more higher demands to make room for liquid storage, where snow runoff is slower and they store it and it keeps the peak flow downstream of the dam. So can you explain how that mechanism is working?
Well, the best answer would be from Michelle Stern paper on that topic. The mechanism, my reading of the paper is that basically with more rainfall, less snow, the input of moisture is being spread out over a greater period of time, and so the peak flows therefore tend to be less.
Thanks, Dave. That was I learned a lot from that.
Good.
I'm supposed to know everything already. The reduction in the sediment source for the delta. I understand the effects of reservoirs and the depletion of the mine tailings. How about the leveeing of the system? We now have rip-wrapped levees up and down the system instead of sheet flow over larger floodplains. How much of that is immobilized sediment in the valley and kept it in place?
In the papers we've done, that's certainly one of the contributing factors, that as we stabilize the levees for obvious reasons, one of the things that does is it prevents meandering of the river. So the river would used to cut into its banks, mobilizing sediment and bringing that downstream. And as it's something, the papers have the exact numbers, but it's something like half of the Sacramento River banks have been levied in the past, or rip-wrapped in the past 50 years to stabilize them. And that, again, prevents the meandering and decreases the sediment supply. You can think of like the Yolo bypass as being a floodplain that, in a geomorphic sense, at some point the river would cut into that, remobilize all of that sediment in the old floodplain, but we obviously aren't going to let that happen anymore.
I guess I'm also guessing that sediment is moving out of Cache Slough today.
Yes, that would be the case. Yeah. Mm-hmm.
So they asked me to stand, and I learned a lot too. Thanks so much. But I'm not supposed to know anything, so this is probably a really dumb question. But in your looking at the relationships between turbidity and submerged aquatic vegetation, you seem to be concluding that it was an increase in vegetation that's associated with the reduction in turbidity, or seemed to be driving the reduction in turbidity. But isn't it also possible, or how do you tease out whether or not the reduction in turbidity allows better light penetration and enhances the growth of SAV?
Well, there is a positive feedback there in theory, where if you have a reduction in turbidity, you have more SAV. If SAV grows, then it can trap more sediment and clear the waters further. So there certainly is a positive feedback loop that is hypothesized for the delta. And that seems to be one of the big drivers that over the next few years, in terms of the sediment, we'd like to get a better handle on. Yes,
Dave, I've been walking along the river almost every morning as I come to work because I'm fascinated by what's going on. One of the things that you note is the tremendous amount of flotsam and jetsam that's coming down and being floated. Can you tell us anything about what happens to all of that large organic matter that is transported down into the delta? Where does it end up residing?
Well, we have not specifically studied that, but I can speculate. A lot of it seems to get hung up on our instruments, for one thing. We've pulled up many trees and things from instrument tripods that have caused trouble, and usually we lose a station or two during this type of event. A lot of that gets hung up in sort of the dead zone areas, or gets flushed out to the bay and the ocean. And what percentage actually is retained in the system, and what percentage goes out, say, to the Pacific Ocean, I have no idea what that fraction would be. That would be an interesting question. But certainly we see this, you see that material out in Suisun Bay, Central Bay, as that plume spends about what is now about next week progressing toward the Golden Gate.
I guess I'm supposed to stand also. Can you comment on, you made some generalizations about the delta per se and reduction of turbidity or sediment loads, however we want to interpret it. What about Grizzly Bay? Can you comment on what's happening in Grizzly and Suisun? Is it just going to be the same that's happening in the delta, or is there any difference because you're that much closer to the bay?
In Grizzly Bay actually is an interesting place because in the 1990s, John Bureau and I did some studies out there. We have fairly detailed measurements of sediment concentration in Grizzly Bay, and about 3 or 4 years ago, we went back to Grizzly Bay to some of those sites and reoccupied some of those sites and to compare the concentrations. And essentially there has been, again, about a 50% decrease in sediment concentrations collected during the fall period, during the same time of year, during that sort of quiescent fall period at the end of the wind wave season and before the flows. So we have seen decreased concentrations in Grizzly Bay and throughout San Francisco Bay. Yeah, thank you.